Welcome back, students. Now let's go to section 3 of this notebook, derivatives and graphs with some computation. The first class of problem is the absolute extrema. What is so-called the absolute extrema? We have a bunch of local maxima and minima, and also the endpoints of the interval. Among those, simply take the highest value and the lowest value. The highest is the absolute maximum, and the lowest is the absolute minimum. So theoretically speaking, in order to find out the absolute extrema, you have to find out all the local extrema. So at first glance, this is harder, but in actuality, no, it's the other way around. It's easier because you do not have to test whether a given critical point is local maximum, local minimum, or neither. Simply take them all and then calculate them all, maybe 4 or 5 of them, and then take the highest and then take the lowest. Also, you can always plot the graph like this. If you have a graph in front of you, then you can make an educated guess. And that makes the problem so much easier. Here's a problem from -1 to +1. So we have two candidates here, endpoints of the interval, and looks like there's another candidate down here, local minimum. That's when the derivative is going to be 0. So let's find them all. Take the derivative and set it equal to 0. And what do we get? We have x equal to -1 or x equal to 1/3. Let's go back to the graph again. X equal to -1 right here, x equal to 1/3 has got to be here. We just test them all. X equals to -1, the endpoint, x equals to 1, the other endpoint, and x equals to 1/3. Calculate them all, and then what do you get? The smallest is this is the absolute minimum, and the biggest absolute maximum. Those are shared by x equals to -1 and x equals to 1. So we can write like f attains absolute minimum -5/27 at x equals to 1/3, and absolute maximum 1 at x equals to -1 and also at x equals to 1. That's the most perfect way to answer this question. That was too simple, wasn't it? Let's go a little bit harder. Kind of like this. Okay, a little bit harder function, probably a little bit harder derivative. Still, x equals to 1 and x equal to e, the endpoints, are automatically candidates. Now, if you take the derivative and set it equal to 0, you may get one or more candidates. How do we do that? Let's begin with a graph. Okay, here's a graph, and then this is the portion we are interested in, x equal to 1, and looks like there's local maximum here, which is also absolute maximum. And here, the endpoint e, that looks like absolute minimum. Well, that's an educated guess. All right. And then let's go to the algebraic expression, and then let's do the computation. How do we do that? It's a derivative computation. Log functions, so entire denominator goes below, and derivative of the numerator, derivative of the inside goes to the numerator. Basically, I'm using this. Of log of u of x. Do you remember this formula? U prime of x. Oops. U prime of x. Sorry about the typo. Over u of x. Just this formula there. Okay. Setting it equal to 0, it doesn't matter what happens in the denominator. So simply the factor the numerator and then set it equal to 0. What do you get? You get either x equals to 2 or x equal to -2. We're in the interval from 1 to e, so I don't care about x equal to -2, this factor. All I care about is x equal to 2, and we have to test those. Run your calculator. It'll turn out that the maximum at x equals to 2, which is about 1.94 something, log of 16 is the precise value, I guess. And the minimum is right here when x is e plug it in. We have log of 8e squared minus e to the 4th power. Run your calculator, you're going to go 1.5 something. A little bit harder derivative, but not too bad. Now this is going to be a little bit harder because this is periodic. We do not have endpoint, goes all the way. Is that going to cause trouble? No, not really. It's periodic, so all you have to do is find all the critical numbers inside one period from 0 to 2 pi or negative pi to pi, whatever you want to do. Here we go. Take the derivative and set it equal to 0. Take the derivative using the chain rule, and then setting it equal to 0, all you have to do is to factor out. So what do you get? The first factor, sine of theta is equal to 0, or second factor, 1 plus cosine of theta is 0. We get these two. Sine of theta is equal to 0, k pi. Cosine of theta is equal to negative 1, pi plus 2k pi. Here's a graph, by the way. See? K pi, all these, and also all these. And then pi plus 2k pi, so only down below all those. So what's the absolute maximum? 2k pi. And even multiple of pi, that's when we have 2 plus 1 plus 1 squared, that's when you have 3. And then absolute minimum negative 1. You can check that with your calculator. This kind of problem, okay, from 0 to 2, that's true, but I have a feeling the derivative is a little bit harder. You may have to solve a quadratic equation of an exponential function. And let's see, we have f of 0 and f of 2 automatically candidates, but the derivative and setting it equal to 0, that looks like a bit of a challenge. How do we do that? Well, here we go. Take the derivative, and we are setting it equal to 0, but the key is to factor e to the negative x out. Oh, okay. So this wasn't as bad as I thought it would be. You don't really have to solve a heavy-duty quadratic equation of e to the negative x power. Just plain factorization worked. So either e to the negative x is 0, or this factor is equal to 0. E to the negative x, that's never 0. Exponential is always positive. So that's out. This is equal to 0, and we get this equation. Solving this equation is just generic. Solve for e to the negative x and take the log. We end up with x equal to log of x. And that's the number you're plugging in. So here's the conclusion. X equal to 0, x equal to 2, x of log of 2. By the way, this is a graph. Maybe you should have looked at the graph before doing this, by the way. X equal to 0, and this one you just did, and x equal to 2 there. Yes. That's a graph. This is just a verification using calculator. X equal to 0, x equal to 2, x equals to log of 2. Just using calculator, no big deal. Now how about the big deal? Here, taking the derivative and setting it equal to 0. Typically you get an equation, so you'll have to factor it because the right hand side is 0. Whatever you factor, you can set each factor equal to 0. Exponential is never 0, so the other factor is 0. From there you get a log equation like this. There's a lot of layers of college algebra here, but if you just consider any one of them, then each one is pretty much straightforward. The combination of everything makes this problem rather hard, but I still wouldn't say it's exceptional. Something you should be able to handle. So much for absolute extrema problem, and we're going to consider 3.2 in a separate video.